Hey guys, with it being so close to Memorial Day, I just wanted to add a few clips, a few pictures at the beginning of this video showing some memorials downtown Augusta, close to where I live. I go by these memorials every day going to work, and it's just awesome to see these memorials and what they reflect. Just so thankful for those who made the ultimate sacrifice. I also want to include an awesome flag in that area that Gander Outdoors put up. Such an awesome display, such a huge flag. You can see it from Interstate 20, and I always enjoy seeing it waving in the wind. Just a small reminder that the fallen, you're forever honored, you're never forgotten, and we're forever grateful. So this was our kitchen fixture that had these 32-watt T8. The bulbs had went out. At least one had gone out, so I thought it might be a good idea. Go ahead and get these Fiat Electric LEDs. Just convert your old fluorescent fixture just by simply replacing the tubes. At 14 watts, I thought, wow, it won't even get the ballast warm. Well, whether it's coincidence or not, put them in, they were bright. Everything was good for about an hour. And what I didn't like was this ballast got extremely hot. I apparently opened up the thermal. Whether it's a resettable thermal or not, I don't know. Or it could have just failed internally. But anyway, even now, with some power hooked up to the ballast, it won't do anything. Because it was up in the ceiling, did the same thing. Just quit putting out like the breaker trip. But had power in, just apparently no power out. So being electronic ballast, maybe we'll look inside and see if we can see why it may have failed. See if it has any likelihood of being something about putting these LED bulbs in it. We'll be back with this electronic ballast on the bench. So I won't dig into this too deep because it's tar. At least it acts like tar. It looks like tar. I just want to look into it a little bit, why it would have failed. As I look into here, I know I'm open between here. I checked across the black wire, and usually what's a fuse or some type of protection device, and it's open or mega ohm. So as I get the prying up, you can start to see that there is a fuse in there. So whatever's going on has definitely blew a fuse. It's not just a thermal protection device issue. And as we look here, we have what appears to be a transistor, like a or TO220 package. We go across the pins here. 1 ohm, less than 1 ohm, less than 1 ohm, less than 1 ohm. So the other side was the same way. I just broke it off. I broke it off to make sure something else in the circuit wasn't shorted. As I go across the actual pins itself, 1 ohm, 2 ohms, Yeah, 2.1 ohms. So this is, if you can see that, it is a E13005, which is an NPN transistor. So whatever's happened is shorted out the transistors as well as blew the fuse. So not pretty. So after looking at it, I'm really glad that the fuse took care of the safety aspect of the component shorting out. Just still very curious about, and that's why that actually happened so quickly after replacing it with a lot less wattage light bulbs. So actually probing across the tip right at 18 to 20K across each set of pins, both sides, both bulbs. So it ain't like one bulb is acting worse than the other, but I might not be able to stand it. I might just have to take one apart and look at it. Went ahead and took one end loose. I just had to. If I gotta slide it, one end had to come loose. And there we go. So both ends had the same input protection. So back now with a GE Proline T8 ballast. It can be a 2 lamp or a 1 lamp. As we see here, the schematic is a little different. It tells us here for 1 lamp just to cap off one of the blue leads, which can be an open circuit of 600 volts RMS. So we have the blue lead capped off. I'm careful to have my ground wire hooked up here with this just leftover yellow wire I had from another job. And I got my 120 volts coming in. And I have my red lead hooked up to a terminal here with both the leads on this end to the same terminal, just like it shows on the diagram. So careful to have our ground hooked up and our power. This is a fused quick tester. Let's see, get this meter up, we can see it a little bit better. So we're right at 42, almost 43 volts AC across the ballast, because it is current regulating. So that's kind of surprising, because remember, this is a 600 volt open circuit ballast, but it's regulating down to the current it needs to be. So it's holding pretty steady, about 43 volts. I'm going to pull the leads off of the AC where it goes in. I'm going to go to DC, and I'm going to carefully go across this capacitor. So about 67, 68 volts. I'm going to get a quick look now at our watt meter. So we see here we got 0.22 amps, 15.9 watts. So 4100K, 14 watt. So hooked up with this ballast, it actually seems to be working pretty normal. But it is odd how the other ballast was wired up differently. But all in all, the LEDs do seem to be working normal, at least with this type ballast that has the individual blue lead going out to the individual lamps, and then just the red wire will be common to both, split off, and the actual ends are tied together. So this ballast is a little bit different. I drew out a real quick diagram for me, just looking at how the layout of the diodes were, how many was in series, how many of those series banks was in parallel, and I made some notes on here, but it's kind of hard to follow. I did this as I was tracing it with my meter, so I did lay it out just a little bit neater in actual schematics. It don't really matter which side it's designed that way. It don't matter which way you flip the lamp, obviously, fixture. Just to compare the way it is on the table with the way I had drawn it out. We see that we come in from the left, going through our thermal fuse or our thermal cutout, and those go through, if I can get this in the shot a little better here. These go through two surface mount 10K ohm, which is a 20K load. Then it goes across the little ceramic caps, and then from there it goes through the diodes, turned opposite way in polarity. So no matter what polarity comes in from which end, we see that the right ones are going to come through, right? So as we come through the diode, it's going to be an AC signal coming in. So one half of the cycle we're going this way, and one other half we're going this way. But anyway, at this point in time, let's say it's the high side of the cycle. It's going to come through, go through this diode. We're going to hit the cap, and the other end's doing the opposite. On the negative side of the cycle, it's going to be coming through, and it's going to be going through this diode and coming through. So we basically got us a full wave fire here, and we're charging up this 22 microfarad cap C5, which is right here physically on the board. So that gives us our bus, and without knowing much about the ballast other than 600 volts open circuit, we had to test it with the load on it. So I knew it was pulling down considerably with the load being regulated. So as we saw in the video, we got around 43 volts in, around 68 volts on the bus of this capacitor. So we're running about 68 volts or so, and we are truly hitting that 15 watt, around 14-15 watts output, so, or energy input, about 15 watts energy input. So everything checks out as it should. I don't believe anything was wrong with either of these LED strips checking them out. It could have been that my ballast was about to go, but it was odd that I put these in and my ballast started acting up and actually got really, really hot and ended up shorting the transistors and blew the fuse, as we seen earlier in the video. But we see here, one thing I didn't mention, this on the other end. I'll take this loose so I can bring it around. I forgot this side wasn't in the shot, sorry about that. As I've drawn it out here, it's very, very similar. We see the layout that's coming through the thermal cutouts, through the 20K ohm load here, going across the caps. And then we have a larger resistor here which says 0. Has a 0 on it, so it's called F1. So they're just using that 0 ohm resistor as actual fuse. They call it F1. So I just wanted to show it here as a 0 ohm F1 coming in. So we basically have almost identical coming in. This capacitor is different on this end, but it's actually used by both sides. They're just coming in, and that's going to be like your filter and your storage bank capacitor right there. But I was really happy to see all these nice LEDs and extremely happy to see it being a 68 volt bus. I really wasn't expecting that. I was expecting this to be a lot higher voltage, similar to TV backlights. If you ever worked on TV backlights, I've worked on several. TVs are not my thing, but I do work on them off and on. Your LED backlit TVs are pretty high voltage, sometimes 350 volts or so. Well, it's a lot more LEDs in series. They're pretty much all in series, so it's a current regulated supply usually on them, similar to this, I guess, but it's a lot higher voltage. So with the 68 volts, I do have an idea what I can do with these for a work light. So I can even say maybe rechargeable or a portable work light. And even though a DC source like my 56 volt Ego battery wouldn't quite be enough to charge this bus up and and fire these LEDs and keep them lit well. We could still, if we wanted to, we could do a step up regulator or a boost regulator, and with that boost regulator we could use the current control part of it, as long as it's got the like a constant current and a constant voltage type boost regulator. Then we actually could hook that up across our bus and actually use this for a portable light if we wanted to. So that might be something I do in the future, because I have these, and instead of taking them back, I thought it would be interesting to look into them and see how they're made. And they're made very well. It's a well constructed LED bar. I really want to repurpose it in the future. So I really wish we could have dug in a little bit deeper in this video, at least a likely reason why that this original ballast that I had did not like driving these LED bulbs, and it could have been that this ballast just failed because one lamp had already went out, and instead of buying fluorescent lamps, I wanted to go ahead and replace it with the LEDs just to see how they worked. I was interested in them, and then I ended up putting up an LED fixture anyway, which was probably the right thing to do, honestly. On the long term, I was either going to put up an LED fixture or rewire my old one to go straight to LED lights, the tubes that take the 120 volts directly. But I thought this was a neat idea and was very curious on how it worked, and enjoyed getting to look at it and see how it worked a little bit deeper. I wouldn't necessarily be scared of these, because with the overheat protection and the fuse here, it's protected pretty good. So something could have internally went on with the ballast to make those transistors short and the fuse blow. I believe something happened internally here. Yeah, the ballast overheated, the transistor shorted, and of course that fuse blew in that ballast. So instead of the type A that uses the ballast, they call it the type B that you wire up directly to 120 volts. Change your wiring and just remove the ballast altogether if you want to keep your existing light fixture. Well guys, I wanted to come back and add this part to the video. I do now have a Sylvania. It's a rapid start ballast. This is just a one lamp ballast. It's not the same ballast that I had in my fixture that I tried these LED bulbs on first, but it actually is kind of hard to find a rapid start ballast now, so I got a hold of this 120 volt single bulb that's also a T8 rapid start electronic ballast, so it's pretty similar to the one that I had. So I thought we'd just hook it up, because it does hook across the 20K resistors, and of course comes through, and one pin is going to actually power up and the other one's just going across our 20K ohm resistors here. So that's the difference in the rapid start and the instant start ballast that I've seen. So we do see here how it's a little bit of a difference. So I just thought we'd hook this one up and just see how it does. Got somewhere around 13-14 watts. The brightness looks okay. Brighten up this video a little bit so we can see. We know we should be getting somewhere around 40 to 45 volts out from our last test with the instant start. And man, we're right on the money with 42.5, 43 volts. And actually across the ends, we're getting about 1.2 or 1.3 volts. Yeah, a little over a volt to 1.2 volts that the rapid start usually uses. So it's just going across this 20K ohm load. It's doing nothing more for us. It's just, of course, the one line that's actually supplying the power we need for our bus. And that voltage looks good. So if I go to DC volts, I look for this capacitor, the DC bus, to be somewhere around 68 volts. Be 66 volts. So we're very, very similar to the instant start ballast. I just wanted to mention that we are now at 18.6 watts. So the wattage has creeped up. Just showing 0.15 amps. So under 19 watts, but the watts does show a little bit more for the rapid start ballast. It is actually getting warm to be nothing but, you know, less than 20 watts going through it. We'll let this run and I'll be back. I did also want to take time to show the frequency difference. Not taking time to get a scope or anything out, but somewhere around 32 kilohertz. 60 hertz on our input. So that was just to show that the frequency makes a big difference in actually the filtering part of this. So we don't have a lot of capacitance as our storage, even though this is just an AC signal coming in, but it's at a very high frequency, so you got to take that into account. And I just mentioned that because, as you'll see in this little clip, I just took a variable transformer, my Variac, and I just hooked it up to a voltage to get our DC bus. But you can see a little more flicker in this video. You can see that flicker because we got 60 hertz and not 20 to 30 kilohertz coming in. So we know that that makes a big difference on the filtering part of that circuit if you wanted to power it, just say from an actual transformer or a variable transformer like I showed. Not that it's not that it isn't possible, but it's going to have more flicker and it's not going to perform as well than this higher frequency output. Around 150 degrees, got to be a transistor on that side. Real similar to the same temperature as before. It's been running about an hour, so at least it's not just constantly getting hotter. After it's been running about 10 minutes or so, it got hot enough for me to be concerned, but apparently its temperature's not still rising as it runs. So we see some results from testing this particular rapid start and the previous GE instant start T8 electronic ballast, that this rapid start did run 2 to 3 watts higher, but still the current and the voltage and all look good on the LED strip. Just possibly the way that the rapid start goes across for the bulbs that typically heat up on the ends might just give you an extra watt or two loss, apparently from using the rapid start ballast. So I think mine was just a coincidence. Either it was already going bad or I just had a non-compatible ballast with this type lamp. I did actually try to find one similar, and I just didn't have any luck even to use one on eBay or anything at the time of this video. But I would have liked to have found one just like it and been able to hook it up and try it. But apparently it wasn't anything to do with it just being a rapid start instead of an instant start ballast, which was good to know. So I wish we could have got into it a little bit deeper. But for now, all we know is this ballast died trying to run them. But it appeared to be fine on the bench, and I don't see why it wouldn't have been fine. So since I'd had issues with my LED lights and my fluorescent fixture, I just thought we'd look into it a little bit. And after I got to looking into how it's made, kind of got sidetracked into looking deeper in it and how it works. If you like this deeper look into this LED replacement lamp, please like, share, subscribe. Thanks for watching.